Hello and welcome back. In this video, we will be discussing the coefficient of determination, or R squared. Okay. All right, let's start off with some vocabulary. First off, the coefficient of determination, R squared. This is the proportion of the variation in the response variable that is explained by the linear regression model. Okay. And we have an equation given for this, R squared equals SSR over SST. We'll go into what these mean shortly. All right, next up, explained variation. This is the part of the variation in the response variable accounted for by the regression line. Unexplained variation, the part of the variation not explained by the regression model, often due to other variables or random error. Coefficient of correlation. If you had not watched this video, I recommend going back and doing so. But our coefficient of correlation R is it measures the strength and direction of a linear relationship between two quantitative variables. And we should notice the variable we use for a coefficient of correlation is R, where our coefficient of determination is R squared. We're going to go into that later too. Next, residual, another one. If you have not watched this video, I recommend you do so. Our residual is our actual y value minus our predicted y value, given with this simple equation here. The equation for this is y minus y hat. The little caret on top of the y is called y hat, and that's what we use for our predicted y values. We should also recognize that from the least squares regression line. All right, so the letters we saw above before, they're introduced over here. First, we have the sum of squared errors, SSE. This is our total unexplained variation, and it's given with the equation as the summation of the residuals squared. Okay, we should recognize this from right here. We square all these values and add them up. Next is the sum of squares total, SST. This is the total variation in y, and it's given with this equation here. Summation of y minus y bar squared. We should recognize y bar from the sample standard deviation and sample variance videos. I use x bar in those. Bar means the mean, so this is the sum of y minus the y mean squared. We take all the y values, average them up, and we use that number to calculate all these. We'll go into an example, but just give a heads up. And lastly, sum of squares regression, SSR. This is the explained variation, and it equals SST minus SSE, so it's the difference of these two values. And this is also known as explained sum of squares. Not super important, but you might see this terminology thrown around as well. All right, let's take a look at an example. Here we have a data set. Hours studied, corresponding quiz scores. Okay. First step, we need to find the least squares regression line. I have a video on this. I'm not going to show all the steps to find that. If you don't know how to find this line, go back and watch that video. Or if you know how to do it with a calculator, which I show you how to do in another video as well, check those out. But if we find the least squares regression line for this given data, we should get y hat equals 5.4x plus 46.8. Also, I made a note here, equations may slightly vary depending on what you use to come up with the equation. It might be slightly different. I actually used two different pieces of software to compare, and I noticed both of them gave me slightly different equations. If they're close enough, it's fine. It doesn't have to be super exact, but just be aware certain software might give slightly different answers. Anywho, step one, find this equation. Step two, use the equation to find predicted values. So these are our hours studied, these are our test scores, and these are our predicted test scores using this equation. Simply plug each x into the equation here to get the y hat value. That's where we get all these. So if we plug 1 in, we get 52.2. If we plug 2 in here, we get 57.6, etc. All right, step 3, find the residual. The residual is the difference between y and predicted y hat. So y minus y hat, 52 minus 52.2 gives us negative 0.2. 57 minus 57.6 gives us negative 0.6. 63 minus 63 is 0, etc. We see the idea here. All right. Step 4, square each residual. Take each value from the residual column and square it. Negative 0.2 squared is 0.04. Negative 0.6 squared is 0.36, 0 squared is 0, negative 2.4 squared is 5.76, and 0.2 squared is 0.04. All right. So next we calculate the sum of squared errors, our SSE, which is summation of y minus y hat squared, which means we just take the sum of the residual squared column, okay? So we add up all these values, 0.04 plus 0.36 plus 0 plus 5.76 plus 0.04, all of them listed here, equals 6.2. So this represents the unexplained variation in the data, okay? Step 6, find the mean of the response variable y. So the mean, it's simply add up the values and divide by the number of elements. I write that here, summation of y sub I divided by n for number of elements. Our y values, we have them all right here. Add all these up. 52 plus 57 plus 63 plus 66 plus 74, all of that divided by 5, we should get 62.4. I didn't show the part where I add these and then divide by 5, but just trust me, bro. All right, anywho, y bar, 62.4, that's our mean of y values. Step 7, compute the sum of squares total, our SST, which is the sum of y minus y bar squared. So we have to make more columns. Here I have the y values given. This column here, I do y minus y bar. Again, our y bar is 62.4. You see me right? I showed the steps here just so it's a little bit more clear. Y minus y bar, 52 minus 62.4 is negative 10.4. 57 minus 62.4 is negative 5.4. 63 minus 62.4 is 0.6. 66 minus 62.4 is 3.6. And 74 minus 62.4 is 11.6. And then we need to square them. So we take all the values we found in this column and square them to get the values in this column over here. I'm not going to read it all out. I'm sure you could see the work right here. And then the summation means we add all these up. I show that over here. Summation of y minus y bar squared is 108.16 plus 29.16 plus 0.36 plus 12.96 plus 134.56. We add all those up and we get our SST equals 285.20. And this represents the total variation in the quiz scores, okay? All right, almost there. This one's lengthy. Step 8. Compute the sum of squares regression, SSR. This is easy. Once we found SST and SSE, which we found already, we just subtract the two. Our SST we got right here, 285.20 minus our SSE, which we found all the way up here, 6.20. Subtract the two, and we get our SSR, sum of squares regression, 279. And this tells us the variation by the regression line, okay? And our last step, finding R squared. Now that we have SSR, we divide that by SST. So our SSR was 279, our SST was 285.20. We divide them and we get roughly 0.978. And that is how we find our coefficient of determination. Now, I know that was fun. I'm sure we noticed that the correlation coefficient is denoted as R, and the coefficient of determination is denoted as R squared. We didn't get there yet, but I'm just going to spoil the fun. What if you find the correlation coefficient R and simply square that value, you will get the same, if not a close enough value. You don't have to do all this. You could just simply square your correlation coefficient. So then you might ask, why on earth would you do this? A couple of reasons. Number one, it's good to just be familiar with it. To be honest, this is something that was new to me. I had to teach myself this before making the video, just because I want to be familiar with it. Sometimes you're going to be tested on particular knowledge, on a particular way to do things. Another one is, as one of my professors so elegantly put it, respecting your ancestors. Out of respect for those who figured this out, we should know it. But this to me is one of those things that, like, you might see on an exam just so your teacher or professor makes sure you know how to do it, but in all practical sense, you're not going to do it this way. Anywho, all right, so what does this mean? Okay, so this is where explained and unexplained variation come in. This number tells us about 97.8% of the variation in the students' test scores can be explained by the linear relationship between hours studied and test scores. Explain variation. The remaining 2.2% is unexplained, meaning it's unaccounted for. But this pretty much tells us that there is a strong relationship between hours studied and what your test score is going to be. Yeah. Oh, here we go. I mentioned it over here, what I just said. So what is R squared? The coefficient determination R squared can be found by just squaring the correlation coefficient. R squared equals R squared. Be mindful of the parentheses. We want this thing to be positive. If some R can be a negative value, when you square it, it must be positive. R ranges from -1 to 1. R squared will always range from 0 to 1. This is definitely the easier method. And just be mindful, answers may vary slightly due to rounding errors. If you're off by 100th, 1,000th, don't sweat it. If you're off by a 10th or in your ones place, that's worth rechecking your work. And here's what something like that would look like. We have our study test score. The points represent the data given. The line is the least squares regression line. And our R squared being close to 1 tells us that all the points are very close to the line, which means using a prediction model will be highly accurate and things like that. There we go. The closer the R squared value is to 1, the closer the regression line is to the response variable. All right. So, and also just a little bit on comparing our correlation coefficient R and coefficient determination R squared. R tells us the strength and direction of a linear relationship, and it's between -1 and 1. R squared tells us the percent of variation explained by the regression model, and it's always between 0 and 1, or you can interpret it as 0 to 100%. Right. Some common mistakes: confusing R with R squared, forgetting to square R, thinking R squared tells us the direction of the relationship, has nothing to do with the direction, and interpreting R squared as a percentage without converting to percent, meaning if you get R squared, let's fix that. If you get R squared equals 0.98, this is equal to 98%. It is not equal to 0.98%. Remember, you have to multiply it by 100 or just move the decimal place over twice. All right. Some practice problems. I got a handful here. I'm not going to read all them. Feel free to pause the video and read them. And yeah, take a stab. All right. Hopefully we pause to work on these problems. Let's take a look at the solutions. Number 1, if R equals 0.8, find R squared and interpret it. So I went with the easy way of just squaring it. R squared equals 0.8 squared equals 0.64. And this means about 64% of the variation is explained by the regression model. 2, if R is -0.6, find R squared. Okay, so I just wanted to show this one just as a reminder to keep the negative in the parentheses when we square. We should get a positive 0.36 or 36%. 3, if R squared is 0.64, what percentage of the variation is explained? That is the explained percentage. 64% of the variation is explained. And that would mean, what, 36% is unexplained to give us 100 in total. 4, what percentage of the variation is unexplained? Here we go, when R squared equals 0.72. Okay, so R squared is 0.72. We do 1 minus that value, which gives us 0.28, which means 28% is unexplained. 5, explain the difference between R and R squared. R measures the strength and direction of a linear relationship. R squared measures the percentage of variation in the response variable explained by the regression model. 6, why are residuals squared? To keep them positive. Yep, to prevent positive and negative errors from canceling and to penalize larger errors. 7, what does SSE measure? SSE measures the unexplained variation. And lastly, 8, what does a small SSE imply about R squared? A small SSE generally leads to a larger R squared. Anywho, thank you for tuning in. As always, a link to the notes will be in the video description, and I will see y'all next time. Take care.